Alright guys, this video is going to be for lesson 6.1 part 1. It covers exponential growth and decay and the graphs of those kind of functions. So we have a question here about what are some of the characteristics of the graph of an exponential function. I'll type these out for you so that way you have them. And if you want to pause at any time to kind of please do. Characteristics of an exponential growth function. Exponential growth goes from left to right. Is increases really fast. An exponential decay function gets smaller. The y values get smaller, so it gets smaller from left to right. So exponential growth is like money at a bank. So when you put money at a bank, it'll grow pretty quickly. Talk about rapid population. That's a popular one. That's going to be another one that is going to be start off with a couple of rabbits, and then eventually you have a massive amount of rabbits. And there's one more again, in age, which is a virus. One virus, and then how quickly does it spread? It could spread really quickly, like the coronavirus. I think like 90,000 people in just a few months. So these are all examples of exponential growth. Exponential decay. Examples of that would be something like the price of most cars. Some cars actually gain value, but most cars decrease in value. So the value of cars. Let's see. Another thing would be a antidote to the virus. So once we start inoculating some of the people that got the virus, the population that's infected actually decreases pretty quickly. And then let's see. Let me give you one more, but I'm thinking. Which kind of relates to the antidote to a virus for population. Medicine in a body is another one. When you take some Tylenol, it stays in your body and then decreases over time. Still always a little bit of a trace of it. So those are some examples of exponential growth and decay. Now we're going to evaluate the expression for x equals -1 and x equals 2 just as a warm-up to make sure that we kind of know what we're doing. Let's go to we're evaluating x equals -1. We got 6. Remember that a negative exponent means the reciprocal. Instead of 4 to the -1, we're going to have 6 plus 1 over 4. Those together, 6 plus 1/4 is 6 and 1/4. So that is your answer. And you could do other forms of that, like 6.25 or 25 over 4, but any of those would be fine. So now let's go and do, this is when x equals -1. So now we're going to go and do when x equals 2. And when x equals 2, we have 6 plus 4 to the second power. 4 to the second power is 16, I believe, and that's 22. And the only reason that you would really need to know these is when you're starting to look at graphs and you have to start plotting values on the graph. And you can do these with the calculator by looking at the table on the calculator, but you can also do this by hand too. So with that said, you don't necessarily have to work with a partner because you might be watching this on your own, but please pause and take a minute to see if you can find which one is which graph here. You're welcome to use a graphing calculator if you like. You're welcome to not use a graphing calculator. Just try to figure it out on your own. Go ahead, please pause and try that on your own. Okay, so before I look at any of these, I'm going to look at this part, and this part, and that intercept, and this intercept, and this intercept, and that point. So just for these, I'm noticing that I am actually getting it by 2. It looks like I'm multiplying by 2 here. So like this one was, what I mean by that is I had a point 0, 1, and then that became 1, 2, and then that point became 2, 4. So what's happening are these y values are being multiplied by 2. Okay? For this one, it looks like if you're going from 0 to 1, and now you're going from -1 to 3, this looks like it's being divided by 3. The reason I say divided by 3 is because if we're going from left to right, we are taking these two numbers, two y values, and we are dividing by 3 each time. For this last one here, not really the last one, but for this next one, 0, 1 to 1, 4, I mean, that's a huge jump. That is actually being, if you're looking at these y values, that is being multiplied by 4. So that tells me that for the first couple of them, A is going to be A. I don't know what B is yet, but C is going to be C. Now let's see the rest of these. So A is A, C is C. Let's see some more of them. Let's go and look at D, E, and F. So D here has this coordinate and that coordinate and that coordinate, and each one of these is being divided by 2 each time. The way I know that is I have -2, 4 here, I have -1, 2 here, and then I have 0, 1, and it looks like each of these y values is being divided by 2. So to go here, divided by 2, and to go there, divided by 2 each time. And when we divide by 2, that's another way of saying multiplying. So let's just make a note here. When we divide by 2, that means multiplying by 1/2. And we could say the same thing on B. When we divide by 3, we are actually multiplying by 1/3. For this next one here, it looks like I have -1, 4. And these are two very easy points I was able to see on the graph, 0, 1. And to go from one y value to the next y value, I ended up dividing by 4, or multiplying by 1/4. And then finally for the last one, it looks like I have, let's pick a different color here. I have this point, which is again 0, 1. And then I have another one, which is 1, 3. And to get from the one y value to the next one, you have to multiply by 3. So what that means is that this F is going to be for B. Okay, for D, where I divided by 2 or I multiplied by 1/2, that was going to be D. For E, where I multiplied by 1/3, that actually ended up being B. And F, where I had to multiply by 1/4, was E. Okay, those are the answers. Let's keep going. And feel free to pause and rewind if that didn't make as much sense. Okay, this is the generic, right from the book, examples of growth and decay. Again, just keep in mind that growth grows from left to right, so the y values get really, really higher as x gets bigger and bigger. The decay, same thing, but flipped in the sense that you start with really big y values and then they get super small and they have that kind of curve. We're not going to talk about domain and range in this video or at this time yet. So to tell whether each function represents exponential growth or exponential decay, you could use a graphing calculator, so that's one. And if you use a graphing calculator, you are welcome to type in 2 to the x. And I'll go ahead and not use a graphing, I'll go and type this into mine. Let's see here. 2 to the x. And growth, because it has that shape, it's growing to the right. So, and if you want to, you can make a table to Plug in 2, you get 2 squared, which is 4. 3, you get 2 times 2 times 2, that's 8. And if we plug in 0, 2 to the 0 is going to be 1, because anything to the 0 power is 1. And if we plug in a negative 1, that's the last one that I'll do, just reviewing your properties. 2 to the negative 1, remember we did that earlier in the warm-up. If you raise a number to a negative power, we do the reciprocal, so we get 1/2 here, or 0.5. So we could graph this. And we get 1, 2, 2, 4, 3, 8, and then we get 0, 1, and negative 1, 1/2. And as long as you're just kind of like finding what that curve looks like, that's fine. You only need a couple values to plot it. And again, you're welcome to use your graphing calculator. I'm not asking you to plot these by hand. So let's go and do the next part. Just going to get this cleaned up for you here. So now to do B. So again, we could graph B and see what this looks like. So this looks like a decay function because we had very high y values here, and they're dropping very quickly. So this is decay. And I'll leave you guys to plot this one on your own. But again, you can use your graphing calculator to do so. Let's go to example 4. Okay, so the value of a car y can be approximated by the model y equals 25, parentheses 0.85t, where t is the number of years. Now, whether the model represents exponential growth or exponential decay. Now, we're going to talk about this a little bit tomorrow, but if you have something like a to the a number that's bigger than 1, so a number that's bigger than 1, to some variable, this is growth. Maybe if you have a number less than 1 to some variable, that's going to be decay. And we could plot this if you wanted to. So 25 to the 0.5 to the 0.85. So you can see here that this looks like a decay function. And the reason it's a this number is less than 1. So we have exponential decay here. Next, to determine the cost of the car, it's going to be 25 0.85 to the 4th power. And we'll plug that into our calculator and get whatever we get here. And we need to make sure that we put the actual units here. So this is going to be $1,000 as our answer. What that means, and we'll talk about this a little bit more tomorrow, is that means that we're going to be losing 15% of the value each year. Which brings us to 13.050, which is about $13,050. The answer here is 13. Now, you want to know when the car is going to be $8,000 in part B, so there's a couple ways you could do this. You could just plug in some numbers for t. We see what the value is when t is equals 4, you get $13,000. We know that if the graph is decreasing, if we are getting smaller and smaller money value, we need to have a higher t value. So let's just t equals 6 is going to be 9,000. So that's good. T equals 6 is going to be 9,000. That was just a $9,428. Equals 7 looks like. 7 is 8,000. That's perfect. T equals 7 is 8,000. The actual number, $8,014, which is a pretty close approximation. Estimating, that's great. Answer, T equals 7. 7 years after the value of the car should be $8,000 if we're losing 15% a year. Watching, hope this helped.